Entropy for the discrete case for discrete random variables. We'll now be studying what is known as differential entropy, which is just an extension of entropy for the case of continuous random variables. And if capital X is a random variable whose PDF f and has a support of x, so this weird symbol x, which is indicating the support of the PDF for the random variable. So then we can define the differential entropy small h of x. So notice that whenever we're talking about the discrete case, we typically use capital letters, and when we're using the continuous random variables, we generally use short case or lowercase notation. So this is given by the integration over the support of minus fx log of fx. Now this is exactly the same formula as we'd seen with the discrete case. The only difference being that instead of the PMFs, now we're dealing with PDFs, the probability distribution functions. Let's try to do the calculation for the differential entropy for uniform distribution. The PDF of uniform distribution, where support is given over the range a comma b, is given by the PDF is given by 1 over b minus a. Thus, we just plug in the value of fx, the PDF has 1 by b minus a, and we can write the entropy of x as the integration over a to b of minus 1 by b minus a log of 1 by b minus a dx. So you should notice that there is no term of x here. Thus, all of this can be treated to be constant, and effectively what we'll end up with is constant times x after the integration, and that has a limit of going from a to b, and that x limit going from a to b would be b minus a. That will get cancelled with the b minus a over here and multiplied by log of 1 by b minus a. So which is minus 1 log of 1 by b minus a, which is just log of b minus a. Generally, we use base e here, the natural logarithmic here. Let's do the same for the 1D normal distribution. Here the PDF is given by 1 over root 2 pi sigma square ips e to the power minus x minus mu whole square divided by 2 sigma square, and the support is from minus infinity to infinity. Again, we just substitute the value of fx in this expression, and I'm not showing the entire calculation, but if you complete this entire expression, you should be getting logarithmic base e of sigma root 2 pi e, or we can write this as half logarithmic of 2 pi e sigma squared. And similar to the 1D normal distribution, we could also derive an expression for the differential entropy of a multivariate Gaussian, where we say that x is normally distributed in n dimensions. That is why I've written distributed in n dimensions small n, indicating the n number of dimensions, where the mean vector mu and a covariance matrix sigma. Here the differential entropy can be calculated to be half logarithmic of 2 pi e to the power n multiplied by the determinant of the covariance matrix. You can put n equal to 1 and verify that this multivariate Gaussian differential entropy that we have shown here is holding true for 1D Gaussian, 1D normal distribution also. Let's try and see some examples of multivariate Gaussian and try to see what the differential entropy would be. If we say the mean vector is, let's do the derivation, let's do some calculations of bivariate Gaussian. So we have, and we assume that choose the mean vector to be zeros and the covariance matrix to be 1 0 0 1, so there is no correlation between the two dimensions. We can calculate the entropy as half log 2 pi e to the power 2, since we have n equal to 2, and the determinant is 1. right? So this is what we have done is for, there is a small typo, this should be x1. So this is the first random variable corresponding to a bivariate distribution. On the right hand side, we have looked at another random variable corresponding to another bivariate distribution. The mean is still the same, and the covariance matrix has some correlation, so it's showing some correlation terms between x1 and x2, which some correlation. So we can calculate the differential entropy for the random variable x2 to be half log 2 pi e to the power 2 and 1 square minus 0.5 square, which is the determinant. And which of these two random variables do you think has more entropy? Again, without doing any maths, if you just look at the covariance matrix, you should be able to figure out the answer. The answer is x1 because there is absolutely no relation between the two dimensions. Whereas for x2 random variable, there is a positive, reasonably strong correlation between the two dimensions. So the amount of entropy is less. We can also mathematically just prove the same. We can calculate the difference between, so we've written h of x1 and h of x2, which is half log something something and half log something something. If we do 2h of x2 minus 2h of x1, that is logarithmic of 2 pi e to the power 2 into 0.75 minus logarithmic of 2 pi e to the power 2 into 1. And we use the formula that log a minus log b is log of a over b. Thus, we can calculate 2h x2 minus 2h of x1 is negative, which means that the entropy of x1 is more. Now we have talked about conditional entropy for the discrete random variable case. The definition for the continuous random variable case is fairly similar. So we say that let x and y be continuous random variables with a joint PDF of f x comma y. Then the conditional entropy of x given y is integration over the support of x and y of fxy, which is the joint PDF, times the logarithmic of the conditional PDF or the conditional distribution of x given y. And as we had shown for the discrete random variable case, we can write h of x given y to be h of x comma y, which is the entropy of the joint minus the entropy of the random variable y. So another way to interpret or understand these entropies, the conditional entropies, etc., is to look at Venn diagrams. So this is again similar to the Venn diagrams you would have seen for understanding conditional probabilities and Bayes' rule. So I'm going to first draw a circle. I have here denoted as capital H of x, where capital H would mean discrete entropy, and for discrete random variable, all of these diagrams will be the same for continuous random variable case. All you need to do is to replace capital H's with small h's. So I've here shown just drawn a circle showing the differential entropy for h of x, and I can similarly draw a circle showing the differential entropy or the entropy for the discrete case for the random variable y. And now I'll start marking some things. So first in red, I'm showing the conditional differential entropy of x given y. And similarly, we can draw the conditional differential entropy of y given x, shown in green. And the area in the between, which is the intersection of these two random variables, is generally denoted by I of x semicolon y, or in some text you would see I of x comma y, which is the mutual information. Now you could write this mutual information as h of x, so h of x is this circle, minus h of x given y, which is, so let's go back, h of y is this, h of x is this circle, and h of x given y is this portion of the circle. And if we subtract this red part from the h of x circle, we'll be left with the mutual information part, which we can do the other way around also. You can subtract out, you can obtain this gray region by subtracting out this green region from the h of y circle region. So thus we can define I of x comma y to be h of y minus h of y given x, or h of x minus h of x given y. And finally, if we look at both the circles, then this gives us the joint entropy over these two random variables, x and y. Let's try and take a trivial example to understand these concepts better. I'll be defining a random variable x, which is a bivariate normal distribution with a mean vector mu. So it's a vector, it's not just a scalar here, and a covariance matrix given by 1 rho 1, which means that there is a correlation of rho. Now, since this is a bivariate normal, we can also write this as x1 and x2 are normally distributed with a mean 0 0 and a covariance matrix, where you can also write x1 is normally distributed with mean 0 and variance 1, and so is x2 normally distributed with mean 0 and variance 1. This is just the marginalization property of Gaussians. Now, if we were to write the joint probability of x1 and x2, which is just h of capital X, it will be given by half log 2 pi e to the power n, where n is 2, and the determinant of the covariance matrix. So the determinant of the covariance matrix is 1 into 1 minus rho into rho. So this turns out to be half log 2 pi e squared multiplied by 1 minus rho squared. Now we can also calculate the entropy of x1 and x2. Now x1 is 1D Gaussian, and its entropy is given by 1 by 2 log of 2 pi e sigma squared, and here sigma squared is 1. So this is just 1 by 2 log 2 pi e, which is the same as the entropy of x2, right? Now we can calculate the conditional entropy of x1 given x2 and x2 given x1. I'll quickly show calculation of the conditional entropy of x1 given x2. So we can write the conditional entropy of x1 given x2 to be the joint entropy of the joint distribution x1 comma x2, or just capital X, minus the entropy of the random variable x2, right? So this can be written as entropy of h of x minus h of x2, and I take, so it's basically this expression minus this expression. So I'll write this as half of log 2 pi e whole squared 1 minus rho squared by 2 pi e. Again, I'm using the identity that log of a minus b is log of a by b. And finally, I can write the mutual information of x1 and x2 to be h of x1, the entropy of x1 minus the conditional entropy of x1 given x2, right? So I've already calculated h of x1, the entropy of the differential entropy of x1, and I've just calculated a while ago the entropy of the conditional entropy of x1 given x2. If I just substitute what I have, I'll finally see that the mutual information between x1 and x2 is minus 1 over 2 log of 1 minus rho squared. Now what happens when rho tends towards plus or minus 1? we'll have a perfect correlation in such a case. And in that case, logarithmic of 1 minus rho squared would be logarithmic of 1 minus 1, logarithmic of 0, which tends towards minus infinity. Thus, minus 1 by 2 logarithmic of 0 would tend towards infinity. Thus, what this is suggesting is that if the variables are perfectly correlated, then the mutual information between these two, or the information that you can acquire about one of the variables having some knowledge about the other variable, is perfect. It's infinite. But what about the case when the correlation tends towards zero? So these two random variables are then independent of each other, and in that case, the the expression would turn out to be minus 1 over 2 log of 1 minus 0 squared, or minus 1 by 2 log of 1, which is 0. So, which is suggesting that if there is no correlation between the two variables, then there is no mutual information between them, which makes sense, because if there is no correlation, then knowing one does not help us to have any new information about the other. Okay, so with this, I'll end this short and crisp lecture series. This was primarily to touch upon some topics which we usually skip, but these can be particularly useful for some advanced machine learning concepts.